Okay. Compared to 5/2. So 5/2 divided by 3/64. 5/2 is 53.33 times bigger than that small area over there. So we can drop it. Okay. So from here, the shear stress at point B of the web plus flange is equal to the shear stress at point E, okay, of the web plus flange. So this will be everything the same, 2.75 times 10 to the power 3 divided by 233/12, 1/8, and then this is 5/2. Okay. So this will be 2.75 power 3 divided by 233/12 divided by 1/8 times by 5/2. 2832 or 2833 PSI. Okay. And then finally, I'm not going to calculate the, I'm just going to write down the Q at the centroid. It's so straightforward. And this is also equal to our Q max. So it's equal to QB or QB of web plus flange plus the width is 1/8. The depth is 3 multiplied by 3/2. Okay, so it is this last section that we are calculating now. Okay, where I shade in pink. So this will be equal to 5/2 plus by 1/8 times 3 times by 3/2 is equal to 9/16. So 5/2 plus 9/16 is equal to 49/16. And then finally, your tau max is equal to 2.75 times 10 to the power 3 multiplied by 49/16 divided by 233/12, 1/8. This will get us 3470 PSI. Okay, congratulations, we are done with shearing stress. Aren't you like woo, we are done, yes? Okay. So as I say, this is the one individual topic that is the most difficult to comprehend. What do you think? Is it difficult? Yes or no? Some of you shake your head, some of you like, don't know yet. I need to see the term test, right? Okay. Any questions before going next topic? Okay, the next topic is so exciting. Okay, I love the next topic. Okay, so let me tell you where we are now in our structure analysis ability. Okay, let me tell you where we are now. Okay. Oh, anyone still copying? Yes. Okay. I do apologize. Yeah, I get excited. I just go crazy. Oh, someone online has a question. Yes.
Eugene, I was just wondering, in these cases, do we automatically consider that the first moment of area at the centroid is the maximum, or do we have to analyze first?
This one is maximum at the centroid because the thickness is constant.
Okay, so if the thickness is constant, is the case every time?
Yes, it will be at the centroid because it's just dependent on the first moment of area. Does that make sense?
Yeah, thank you.
Okay, more than welcome. Okay, as I said, Oh, you're still copying or you're okay? You're okay, thank you. Let me know, okay? Right. So where are we now? Okay, where are we now? Okay. So we have learned two formulas, okay? Two big formulas that we have learned. Let me think, is it too big for? Yes, we have learned that stress X is equal to Px over A plus by My over Iyy Z plus by Mz over Izzz y, right? So I told you guys not to worry about the sign, right? The sign I teach you how to visualize. Yes? So from here, we know that we have a distribution. If I were to draw the distribution now, sketch the distribution. So if this is our normal stress, and this is our, it can be your Y or Z, we realize that, okay, this is just a sketch, just to show you a distribution, that the maximum is furthest away from the centroid. Okay. So this is our centroid. Okay. Just a sketch, okay? I know that this has axial loading, probably the centroid and the neutral axis are not at the same point, okay? So that's our distribution. Then we learn about shearing stress, okay? So shearing stress, okay, I will not put direction for this case, okay? The shearing stress is equal to Vy over Izz Qz E plus by Vz over Iyy Qyt, right? So when we plot this out, okay, when we plot this out, so this is our shearing stress. And this axis over here can be our Y or Z. Okay. We tend to get a distribution doing this. And if this line is the centroid, so what we realize that in terms of shearing stress, assuming uniform thickness, this is where tau max occur at the centroid. Okay. And then if you look at bending moment, it is not at the centroid. This is where you get your what? Your maximum compression, and this is where you get your maximum tension. Okay. So if given My, Mz, Px, Vy, Vz off, you can do this. Okay. Now I'm going to take you one step backwards. Oh, what's next? Okay, what's ahead? So the next thing that's ahead is this. I should have, sorry. I will move this. The next thing that's ahead is this. We are going to combine, so what's next? Okay, what's next? We are going to combine this into an element Okay, and in fact, we are going to do 3D element. There's no 2D in the world. Okay, 2D is only on paper when we learn. In real life, it's going to be what? 3D. Okay, so from here, X, Y, and if this is our Z, right? So this will be, we will have our stress X, we'll have our stress Z, we have our stress Y, we also have all the shear coming in. Okay, basically, I'm going to throw the entire kitchen sink into you. Okay, everything. Then from here, right, we are going to learn how to plot. Okay, I need the other shot now. We are going to learn how to plot what we call 3D mole circle. Okay? So this is normal stress. This is our shearing stress. Okay, so we are going to plot 3D mole circle. So 3D mole circle is not a sphere. Okay, so it's one circle. Then we have another circle. And then we have another circle. So we're going to plot 3D mole circles, and each circle represents each plane. So what do I mean by that? So for example, this is represent your XY plane. This represent your XZ plane. And this last circle represent your YZ plane. Okay. The objective is to determine principal stresses. Okay, is to find stress 1 and to find stress 2. That is the objective. Okay. Now, that is the after. There is something before. Okay, there's something before, which we are going to. So what is this before? Okay. The thing before is this. Pardon me, okay? This is what you see in real life. In real life, you are given a structure like this. In real life, you are given how the loads are applied in what section. We will not tell you, or the analysis will not tell you what is the moment, what is the shear, what is the torsion, what is the shearing force. So what we are going to do now is to determine this. Okay, we are going to determine what is this, what is this, what is this, what is Vy, what is Vz in a combined loading situation. And also we are going to look at the shear stress is equal to Tr over J. This is induced by torsion. Okay. So for the next 2 weeks, we are going to focus on this area. Okay. So there are 3 things that we are going to design as mechanical engineers. Okay. As mechanical engineers, we are going to design 3 things. Okay. So the first one that we're going to design is beams under shear force and bending moment or bending loads. Okay, so we know